Hello, everybody. My name is Hector, and I'm going to talk about scaling fleet. Well, just to present a bit the outline of today, I will try to introduce a bit fleet, the status today, and why fleet. Fleet with gRPC, which is what we are presenting, and improvements, and some experiments that we have performed to validate those results and analysis. First, a bit of about me, right? So I am an engineer at GiantSwarm. GiantSwarm is infrastructure for microservices. I like HPC monitoring and performance, and I have fun playing with distributed systems. So yeah, it's an image of me cutting hammer. Okay, so who haven't heard about Fleet? Any one of you didn't use Fleet before? Yeah, all of you. Yeah. Okay, good. Okay, so I will go quick on this. So Fleet is a init distributed system, right? Which enables to manage systemd units and use ATCD for storage, for persistent and transient storage of all the states of systemd units. With this figure, well, you can get an idea of what is a difference of a cluster of Fleet, right? So as you can see, Fleet use ATCD, has the bottom layer, and I use it for storage and coordination between the different Fleet nodes. And on each Fleet node, we also have systemd to talk, right? So Fleet talk with the machine, with the systemd on each machine, and then the coordination is done via ATCD. The architecture, to give you a briefly summary, is built and based on two main components, which is the agent and the engine. The engine will be what you know as the masters, right? And then the agents will be the workers. On this figure, what I pretend is to show what could be more or less higher availability architecture or organization of Fleet, on which, again, you have ATCD for all the nodes, all the Fleet nodes, and on which you have like three Fleet nodes will represent the core, meaning where I will have all the potential engines that can be used as masters, and on which on yellow, what I pretend over here is to say, okay, we will have always one single master, and well, that can bring some point on failures problems. And yeah, then the agents. Also, I wanted to point out that Fleet on each node use dbus to communicate to systemd and know which are the systemd units and which is the state of these units on each machine. Why or how do we use Fleet? At GiantSwarm, we use Fleet, and let's say that we can deploy microservices, and those microservices are represented as JSON file, like could be like you do it with Docker Compose or something else. So let's say that imagine we have a Swarm JSON that we call, and there we have several components, right? So for us, each one of these components is one of these applications. At the end is decomposed on a unit change, right? So we will have, for each services, meaning 3 services, we will have other 4 systemd units, right? Systemd or Fleet units, which are the same for us. However, there is a problem, right? I don't know if all of you have played with Fleet before. You know that the scalability is limited, and there are other problems that you also might also figure it out. But I wanted to detail a bit and list some of the more important ones for us, and those that they were a pain in the ass in our team. So basically, what we figured out is there is a performance degradation over the time when you are using Fleet constantly. You are, let's say, creating and removing Fleet units, and we saw that there are, for some reasons, there are some orphan systemd units, there are some, let's say, data on etcd, and that creates a performance degradation. So the response times over the time is increasing. That also affects, obviously, to when you run etcd. For instance, etcd set command can also variate, and yeah, that gives us a trouble because we use etcd for everything, coordination and storage. Other problems that we spot, it was about the synchronization, right? So we spot problems in which we have our fleet cluster and we have systemd units running for systemd, but for fleet they weren't running. And then we have to dig into that. We were trying to check why this is happening and everything. And also another problems about synchronization was related to the agents. We have fleet agents that for some reason they weren't responsive, so we couldn't deploy things on those agents, and there were no let's say logs that they were telling us that the agent was not responsive. And limited scalability as well. So, well, this was already stated in the documentation of fleet, in the initial documentation of fleet, that there was a limitation of scalability. And, at the end we saw that there is too many dependencies on etcd. And, basically you can observe, looking at the code, that transient and persistent storage is relying on etcd, but also, let's say, the clustering and all the information about the machines that compose the cluster too. So one of my colleagues, where I will work with, Hugo Tavares, in systemd-conf, he mentioned a phrase that I like it personally. He say, if etcd is sad, fleet is sad, and we are sad too. So yeah, we found out that the having two playing together, etcd and fleet, it was quite a nightmare. And yeah, we also have kind of fail recovery problems, because if your etcd cluster goes south, then we are fucked up. So yeah, we say, and you might ask yourself now, why fleet? Okay, so if you have so much trouble with it, and you were working so hard and you found so many problems, why you still believing on fleet? Well, for us, okay, one point, and you will say, okay, you are using it, so that's normal that you push forward fleet. But okay, so Giant Swarm is using it for everything, for all the infrastructure, is using it in order to have a distributed system for systemd in our infrastructure. But we also love the robustness of the application, right? It's simple. It doesn't have so let's say bugs that you can find typically in distributed systems, but it has these dependencies that make things go slower and make things don't work. But we also love the way of you can deploy applications, right? So with Fleet, if you know systemd, there is no any learning curve, because the definition of applications that doesn't differ between systemd and Fleet. So we found out that people that is not too familiarized how application definition can be like for Docker Compose or like, for instance, if you check with a colleague and say, okay, so you have to define an application using Kubernetes. There's so many concepts around, and if you have a small knowledge on systemd, you can define any type of application. So yeah, we find this part very interesting and simple. And also, well, we love systemd and we like the way it works, and having a distributed systemd was also a very powerful reason for us. For others, well, reasons why Fleet. Other reason could be, okay, you have Kubernetes, you deploy Kubernetes, you use Ignition, you use your cloud config. Those are systemd units. So how you can control those in a cluster-wise, right? So, okay, our intention is, well, you have Fleet and you can use it. Of course, if you are using a big scale, like Google does from 1,000 nodes, maybe doesn't make any sense because it won't scale. But if you have a few amount of nodes, it works, right? And of course, you have to know a bit of all the insights to don't make mistakes and have your master being scheduled in any other node. But apart from that, you can use Fleet to handle or control more or less the state of those systemd units that you create with the ignition and on Cloud Config. As well, we also see another reason why to use Fleet. Well, you can have Kubernetes to schedule your services, your containers, pods in this case, but you can also deploy tasks, right? You need your monitoring tools, and you might not want to use Kubernetes also for this. So another option that you can use, or where we see that you can use Fleet, right? So you have cleanup task, systemd units that they are running cleanup tasks on each node on your infrastructure, and of course maybe you don't need the powerful scheduler of Kubernetes to deploy them. So you can use Fleet for that. So what's next? Okay, so we solve problems. We realized that, okay, we still like Fleet because it's simple, because bring what we need from the distributed systems. But yeah, it doesn't scale, has problems, dependencies, so what? Okay, so we started to dig in our team how we could improve, how we can try to don't break the core, but try to make things look better, right? So we tried to think to reduce HTTP dependencies, to obtain better throughput in terms of units per second that can be deployed and the response time. And also, the more important for us was the amount of units, right? We don't want to have 1,000 nodes. We want to have as less nodes as possible with the maximum amount of units inside of each node, which means use your resources at the maximum. And also, well, you want to improve. We wanted to improve the fail recovery, right? So we have Fleet agents that disappear. They don't work. They cannot connect to them, and you don't know what is going on. So we wanted to improve. Or for instance, you have network hiccups, and that agent or that node goes away. Okay, so these 4 points, including the scalability problems, which one also wanted to improve, were our main reasons that drive what we call like Fleet gRPC, right? So we ended up thinking, okay, so we are using HTTP for communication, coordination, what is there and we can use and it's cool. So, well, we say, okay, gRPC framework, it fits, it's quite fast and might give us a quick improvement. So yeah, so we started to work on that, Fleet gRPC, and of course the communication layer now is replaced, so there is no HTTP to communicate with engine between the engine and the agents. HTTP is still used, yeah. Our intention is to replace as much as possible, but of course you need the persistent storage. So we like HTTP, and we don't want to put too much pressure on it. So we say, okay, HTTP is still there, and we want to keep using it for persistent storage. And what we do also in this, let's say, branch, we store all the transient data in memory. That saves time, that improves performance, etc. Okay, so with this figure, my intention is also to show a bit how it looks, this Fleet gRPC new version, right? So we still have workers, and we still have those 3, let's say, nodes that can play as master. Well, now the coordination, as I say, is done by using gRPC. So all the workers talk using gRPC to one of the masters, okay? And as you can see, the color of the masters differs. So all of them, they can talk, right, to HTTP, but only one, it will be the one that is playing as a master, it will be the one that talks to HTTP, and in this case, it will talk to say, okay, this is the leader, this is the state of the units, and this is the leash on machine of my cluster. That's all, nothing else. So yeah, that will be a bit of a briefly view of how it looks new architecture, and yeah, so we can go again. So we saw a couple of benefits of using gRPC, and also a couple of benefits of the new things that we added into it. So we found out that we wanted to improve the fail recovery mechanism, and okay, with gRPC you have this connection registry which allow us to, which always try to connect, and you can realize if things are going wrong in terms of networking that agent and kind of connect to the master and so on and so forth. We also pretend with this, with the gRPC to have a node which is resistant to network hiccups, right? It can happen that for whatever reason on your infrastructure, the network device goes down and after 10 seconds go up again. So we wanted to survive to this without having to reschedule all the systemd units on that agent to other agents, right? So without creating too much trouble. So we also add fallback mechanism. So in this fallback mechanism, what we pretend is if you have an already fleet infrastructure, right, you don't have the port of gRPC open. So if we ship this into Korea's version, when you start it, if the port is not enabled, even if you want to use gRPC, it will fall back to use the previous version which use etcd. We also add the agent health checks to really know what is going on, if everything is going well. And yeah, this I was testing it yesterday. I wanted to show a demo like saying, okay, if etcd goes down in that agent, we can continue keep working as normally. But I found a bug, and I say, okay, well, maybe let's keep a note ongoing work. So yeah. Another of improvements of this version is a smooth rolling up upgrades, right? What we found is, okay, we can have a state on which we have nodes with gRPC and nodes with etcd old version, and we want to migrate it smoothly and slowly because our operation system has other things to do, and it cannot migrate all at once. So yeah, we tested it in our environment, and we migrated, and actually this version is used in production, and we are really satisfied with the stability and performance. So yeah, we started to migrate, and we have our production cluster with different type of fleet agents, and it worked. It detects when it was some etcd agents was talking etcd, and when all of them they were gRPC, started all gRPC communication. Other benefits. So yeah, what I talk now about the hybrid etcd gRPC cluster. We also improve a bit or change the leader election, the new leader election algorithm. We changed it because, of course, the previous version was using etcd to know when a node disappears, then there is no a key on etcd, so we add a new key, and then this is the new leader. So we changed that because in gRPC, you don't need that. So you just check if your master or leader is there, and you check the connectivity, check the health check is okay, and then you go away and you communicate with him. Otherwise, you change the leader. We also find the benefit of having the TLS communication between agents and the engines, so you can secure your communication of the fleet cluster. So that was also good. And yeah, so now what I wanted to show is some graphs, some plots that we took, experiments just to validate, to show you bit reasons and where we saw the benefits and so on. Okay, so the experimental setup was small. As I say, we didn't have too many nodes, but we have big nodes to use for. So we have three master machines, 4 workers. And those are the versions that we use. Obviously, we use the latest version of Fleet to test, to compare against ours. We use in the first and 2 scenario the version 2.1.2 of etcd, and then we use our tool for benchmarking Fleet NAMI. So the first scenario was about trying to see how fast we can start systemd units with Fleet and comparing the current version with our version. The second scenario was more about resistance. How many units can can stand up the new fleet version in comparison with the old one. And then, well, we try to play a bit with the new HCD V3 experimental mode, of course, 1 or 2 months ago to see which was the benefits, and maybe they could have beaten us, but we figured out that was okay, still good. Okay, so before then starting that, we say, okay, you can think about, okay, I have fleet is distributed system D, so system D is fast, but I mean, how fast? I mean, is the problem of having a distributed system that the coordination makes things go slower, or it's just me that I think that system D should be extremely fast, much faster than fleet itself? So we started to compare, and we used one single node of fleet, and we tried to create 500 units concurrently, and we found out those numbers. And the one that scared me a bit was the third one. So I say, okay, how is possible? I mean, how can take more starting 500 system D units? So the problem is concurrency, right? So we end up trying to parallelize a lot all the operation with system D, and we figured out that there was dbus problems, connection timeouts. We have system D problems, so we spot, they say, okay, so we are safe a bit with fleet, and then we try to do it sequentially. Another thing that I wanted to explain, and we will see now in the next, is the system D linking operation, right? So system D, when you use fleet or when you use system D like barefoot, you have to specify where are the units, and you have to link them to tell them to system D, hey, my system D unit is here, so please link it. So the link operation that is performed by fleet, inside fleet, is the one that doesn't allow to get a fastest performance in all the operation. And this is the most expensive operation. And if you go to your computer and you try to create concurrently 500 units in system D, if you just use link, it will say that it would take more time and more time, because it's talking with dbus, and dbus is also going slower. So we found out that the main problem was there that give us not that much performance that other maybe schedulers or yeah. So well, they started this throughput, and we tried to evaluate how much time it takes to create 3K units, and we found out those numbers, right? So with the current version, you might see that 75% of the units took between 1 and 28 seconds. This is a lot for a production system, right? And if you then take into account the maximum of the whole process is really big for only 3K. So then we play with gRPC, and we found, okay, better numbers, much better numbers than the others, and we wanted to improve, but still the link is behind, right? So the link is one thing that it should be tackled. So how looks the graph, right? So I have here a graph where I created started, and I mean load and start, right? Not start like just turn it up. It's deploy, schedule in one machine, and then please start it. So in green, you can see the difference of performance with gRPC. In gRPC, we finish much faster on the numbers you can see before, while an HCD, it takes longer and is not going to scale at some point. There are some holes here. Those holes here represent the reconciliation loop. Reconciliation loop for fleet is I need to check the state of the cluster. I might have system D units that were trying to be deployed but fail, as we spot in one node with system D. So let's retry, right? So this is a loop that is behind fleet and trying to put all the units in the state that they should be for the user. Another of the experiments that we check is how many units we can have in a cluster. So remember, we have 4 workers and 3 masters, and we wanted to have as much as possible units there to use as many resources as possible. So we figured out that with fleet and the current version, even with playing with a bit with the tweaking and hacking some of the parameters that you can do via CLI arguments, we found out that we couldn't go much upper than 3K units, and this is not too much. And then we play with gRPC, and we found out that we could go more than 20K systemd units and far from that. So yeah, we were happy, and that's this, an example. So I want to state that we are not caring about. Okay, those experiments they didn't try to say, okay, well, we can deploy 1K or let's say 10K units in 5 seconds. No, we found out that the system D-Link was a blocking there, so we try to improve further than that. So yeah, in the threshold, we don't care about that, but we care about how the units were created and how many units I can have in my classes. Because if I have 20K and everything is still good, I can list units, I can check the status, start and stop, then I am reusing my infrastructure as much as possible. We also found out that there were some improvements with using this gRPC version on the resource usage. So here in the first graph on the left, I plotted ATCD, while on the right I plotted fleet. As you can see with current version, ATCD, there is a lot of dispersion in terms of CPU usage. As well, there is also an intense usage of ATCD on some nodes, right? I use just 3, but I could have plotted more, but well, just an example of the whole infrastructure. Okay, so now this is how it looks with gRPC. So as you can see, obviously the leader here is the one that is using them all the resources, while my workers are using as less CPU as possible, which is good because I really want to use my workers to do stuff, not to just have a coordinator there running and eating all my CPU. And yeah, well, also on ATCD, of course, if we are not using it for coordination nor and limiting a bit the storage, the usage will be lower. So yeah, that was about resources. And yeah, well, we wanted to compare, say. We wanted to compare between ATCD 2, ATCD 3, and the experimental mode, and we wanted to check how it performs because you say, okay, those guys, they released gRPC and ATCD, maybe it's going to be faster, and we are doing something that doesn't work. So we tested, and yeah, on the left part, we used the normal fleet with ATCD using gRPC, right? And there is a big improvement already in response time. Also, there is an improvement. The amount of units that can be scheduled is much better than the current version nowadays with the old ATCD, and which is obvious, right? Because we find out also that gRPC is good, and ATCD behind with gRPC works perfect and go quite faster. And then we also compare it with the fleet using gRPC, but using an older version of ATCD. And the things were looking still good, so we want to use ATCD v3. So yeah, as a bit of conclusion of all these things we have been done about fleet and gRPC. So we figured out that give us some, they give us a better throughput, right? We can start faster, we can keep much amount of units in the whole cluster. We lower the use of CPU in our agents. We can include security between agents and workers. We improve the scalability, right? Because before we couldn't go farther than maybe 3, 4K, and now we can go way farther. And yeah, there is no need for those cleanup scripts that you have to run to say, okay, there are some units here, but they don't sit in our cluster, so I have to clean them. So please do that periodically, and some other scripts. So future improvements. So well, what we would like to add, what we would like to push forward. So yeah, we want to use ATCD v3 with gRPC. Obviously, we are still using ATCD for storage, as I say, and persistent storage. And yeah, we want it as fast as possible and reliable. And we would like to add TLS to add some security there. Improve the way fleet currently transfer the unit state between the agents and the engine. And yeah, change the reconciliation loop, which I say was the one that tried to get the desired state of the cluster. And also, we were looking into systemd user, right? Systemd user, you don't need to specify where the systemd units will be, because you are saying to, when you configure the systemd user, you just specify where the units will be. So you don't need to do that. And that will make us to remove the link operation that I mentioned before. It was one of the operations that was blocking us. There is some ongoing work. So the intention, and there is a pull request on the fleet repo, is to get the gRPC without not all the let's say, performance improvement that we have made on this test, right? I will put available the branch that we use for the test, so you can play also too. But we want to start adding this gRPC. The intention is to add it on the master and the upstream version. We also use our tool. There is some open issues. Some of them are fast. Some of them are from Anton, guys from Endocode as well, and some from other guys that try to also improve the performance, and we reuse those modifications as well. Okay, so in Jan's Warm, we are hiring, right? Happy people. Any question? Yeah.
How do the does it work? Okay, cool. How do the agents find the engine, like to connect to through gRPC? Like, how do you discover where the engine master lives?
Okay, good. So this is the part that needs to be stored, right? So you need to keep it persistent. And that way we use etcd. So this is one of the things that we use etcd to check, and we know in etcd which is the leader. Contrary to the current version, the leader doesn't have a TTL, right? So then we don't need to check if the key is always there. So we just check, and the information is there is because it's true. And then we switch and connect gRPC to the new master.
One more question.
There's another question over here.
You on the graphs you showed that, like, with the gRPC version of Fleet, like the CPU load on the master was significantly higher, which means that, like, compared to the normal Fleet plus etcd, why is that? Why is this significantly, like, I mean, you need a bigger machine for the master then, right?
Not really, right? So, okay, it's true that you, with etcd, all the nodes has a higher, right? The master also has a higher because it has to do the reconciliation loop of the whole cluster. So you still have the problem on the CPU usage on the master and etcd. With gRPC, the solution or the better performance is that the workers are not being a lot of CPU usage, and master is still being used because he's still doing the let's say the reconciliation loop, but also you have to add let's say the gRPC communication, which also add a bit more of performance. So the idea and future improvement could be not having a leader, right? Having a distributed cluster of 3 nodes where there is no need for leaders. All of them, they can perform this reconciliation, let's say, loop without having to be the real single master, which obviously, when there is a master, there is always a point of failure at some point. So, yeah.
If anyone has questions, go up front.
Okay, so thank you.